All right. Up until this point, we've been saying no friction, no friction. We're ignoring friction. 5.8 talks about friction, so we can now start using friction. So the first thing we want to talk about is consider a situation here. I'm sitting here at my table with all of our equipment on it for making videos. And imagine you stand up and push on the table. But you're pushing on the table and the table doesn't move. Well, I can do that right now. I can push on the table, but the table's not moving. So here's my applied force pushing on the table, the force of gravity pulling the table down. The table's sitting on the floor, so I have a normal force. But if it doesn't move, what do I know? Well, we can say at rest, right? So my acceleration is 0. Well, that means that my net force has to be 0. So that means there has to be some force here that cancels out that applied force of me pushing on it. Let me make it the same size. So I'm pushing on it, but it doesn't move. Where does that force come from? Well, that force is friction, right? Which we usually use a script F for friction. And in this case, what we're talking about is static friction. And that just means friction that occurs when the two objects are in contact and not sliding against each other, right? The contact surface is static because it's not changing. All right, so now what we want to do is consider a graph of the frictional force versus the applied force. Well, let's look at our free body diagram here. Those are the only forces in the x direction. As long as I'm at rest, those two are equal. So we would just have the line with slope 1. Right? Equal. Because at all points when you're at rest, the applied force is canceled out by your static friction. So the next question is, what happens as you keep increasing the force? Well, I think we all know eventually the force is going to get big enough to make it move. And we're all kind of familiar with this on a day-to-day kind of intuition. You feel like when it starts to move, it jerks a little bit, right? You've finally overcome that static friction and it jerks and starts moving. And it's a little easier to keep moving. And that's actually not a falsehood. That actually occurs. So if we were to graph our applied force versus the frictional force, the static friction matches it the whole time, but then eventually you get this dip and then it kind of levels out. And this is what we call the static friction region, and this is the kinetic. So in the static friction region, how do we describe the value of the friction? The frictional force is less than or equal to the coefficient of static friction times the normal force. All right, this less than or equal to value here is because of this breaking point. This coefficient of static friction is based on this breaking point. And the friction, the static friction can be anything less than that or equal to it. But once you surpass that, it starts moving and you move into the kinetic region. The kinetic region is pretty much constant, right? You have this transition area, but once you're into the kinetic region, you have a similar relationship. You have a coefficient of kinetic friction times the normal force. All right, so why is the normal force in there? Think about this. This is my go-to for this. Like, rub your hands together lightly. Now push them together and rub them together. It's much harder to move them up and down, right? And that's from the normal force of them being pushed together. That's one way to think about it without kind of confusing it with gravity. You can talk about a heavier object is harder to move, and that's because the friction's higher, but that's kind of muddied because you also have it's more massive, so you wouldn't get the same acceleration with the same force anyway. You would get motion, but you wouldn't get the same acceleration. So it's just a little muddied. So I like to do the idea of pushing your hands together to convey that. And I spelled an extra N there in kinetic. All right, I've posted a video also of me doing this with a force sensor and some blocks of wood and trying to represent this idealized graph doing that. So watch that as well. But this is what we have to remember as far as equation-wise with friction. So let's just look at a couple of situations. Imagine just a box sitting on the ground and you're pushing on it. If a 20 kilogram box starts to move when a force is increased, let me move to the next page, to, let me edge out some numbers here, 50 newtons. What is the value of the coefficient of static friction? All right, so let's make a free body diagram. We've got a box. It has a mass of 20 kilograms, so it has some weight, has a normal force. We're pushing with a horizontal applied force. And it's not moving yet, right? Because we're talking about that point where it just starts to move. Like, that's the key in this, right? Is the starts to move. So we're talking about that transition right at the end of static friction. So we can use a standard coordinate system for this. I get that the applied force minus the static frictional force is equal to 0, but it's right at that last instant where it's equal to 0. It's about to go over it, right? So this is our kind of boundary condition, right? We're just about to break out of that region. In the y direction, we have that the normal force minus the gravity is equal to 0. And that's going to be true the whole time, even after it starts to move. So taking our y equation, we've got that the normal force is equal to mg. And from the x equation, we have that the frictional force is equal to the force applied. We're given that the force applied is, did I say 50 newtons? 50 newtons. and that the mass is 20 kilograms. What's the other bit of information we know? We need that friction equation, right? We know that the static friction is less than or equal to the coefficient of static friction times the normal force. And we're looking for this. So what can we combine? Well, if we insert this for static friction, and we're looking at that break point, right? So we can actually use the equality part because we're talking about that break point. I'm going to say that mu s times Fn is equal to the applied force. Well, now these equations are connected, right? Because I can plug this in for the normal force here. We've got the coefficient of static friction times mg is equal to the applied force. We know the applied force, we know m and g, and we can solve for the coefficient of static friction. So my coefficient of static friction is 50 newtons divided by 20 kilograms times 9.8 newtons per kilogram. Look at our units. There are no units. It's a unitless value like our trig functions. All right, for this example, what does it come out to? It doesn't really matter what the number is here, but I'll go ahead and calculate. I got 0.255. In general, this is going to be a number between 0 and 1. True for both the static and the kinetic. There are some weird situations where it's not, but in general, this is true. There are some situations where it can be higher than 1, like slicks on a drag car. You heat up your tires, you do a burnout before you race to heat up your tires, and it makes the rubber tacky and it sticks, and you actually get a mu greater than 1. Let's look at another situation. What if we're on a ramp? And now this is with friction. There's a classic result that's really nice. Imagine that you keep raising the ramp until it slides, and you can figure out what the coefficient of static friction is. Right? So raise the ramp until the box slides. What is the coefficient of static friction if the box slides at 25 degrees, right? So we started out horizontally. We keep raising the ramp and raising the ramp and raising the ramp until the box slides off. So again, we're going to look right at that point where it starts to slide, right? So we're given this equation for static friction, but we're going to look at the limiting case, what I called a boundary before. Limiting case is better verbiage there, where they're equal, right? Just before it starts to slide. So let's look at our free body diagram. Got our gravity, we've got our normal force, and we've got our friction. We said this before when we were introducing contact forces, but it's been a while. We know that normal force, well, normal means perpendicular, and frictional forces is parallel. Right, so parallel to our surface, we have a frictional force. Perpendicular to our surface, we have a normal force. And if we slide, we're going to slide down the ramp. So I'm going to use my tilted coordinate axis here. We've been through this several times. My angle theta for the ramp is the same as my angle between the vertical gravity and my tilted y-axis. So if I look at my equations of motion in the y direction, I have a normal force and I have the y component of gravity. And the y component of gravity is adjacent to theta. So that's going to be Fg cosine theta. And there's no acceleration in the y direction. There's also no acceleration in the x direction because we're still talking about right before it moves. So in the x direction, I have Fg sine theta minus the friction equals 0. And this is a static friction if we want to be explicit. All right. Well, you'll see in this case that the normal force matters, right? A lot of these problems that we've done, we've kind of ignored my sum of forces in the y direction and focused on the sum of forces in the x direction because there was no acceleration in the y, there was acceleration in the x. This time we got friction, so we actually care what the normal force is. So we have to look at the y direction as well. Normal force is mg cosine theta. And let's look at our friction equation. For this case, I'm using equality because we're looking at the limiting case. So here's my y equation with mg plugged in for the force of gravity. I'm going to make the same substitution in my x equation. And I'm also going to substitute in for the friction in my x equation. Now we have this result for normal force that we can plug in. And we get mg sine theta minus mu mg cosine theta equals 0. Divide by mg. Sine theta minus mu cosine theta equals 0. Yeah, this is mu, if anybody doesn't know all their Greek letters. If we bring this to the other side and we divide, we get that mu is equal to sine theta divided by cosine theta, which is just tangent theta. Right, so this is a great result. It's really compact. Like we did a lot of stuff to figure it out, but it's really compact. Just the static friction is the tangent of the angle where it starts to slide. That was a really nice, compact, neat result. For our example, what did we say, 25 degrees? Yeah. So mu, if this box were to slide at 25 degrees, would be equal to 0.466. All right. Anything else I want to say about friction before I end this video? We're going to use friction for a lot of other things. Well, we did static friction examples. Let's do a kinetic friction example. So in this one, let's look at our shopping cart example again. A shopping cart, it has wheels. I don't want to do something like that. Let's just say a box. A box is pushed across the floor. By a force of 25 newtons at a constant speed if the box has a mass of 45 kilograms, find the kinetic coefficient of friction. All right, so let's draw it first. We've got a box. Somebody's pushing it across the floor with a constant speed. What's constant speed mean? Constant speed means that the acceleration is 0. So they're pushing it, so we've got an applied force. It's on the floor. We weren't told the floor is level, but I think unless you're told otherwise, you can assume the floor is level. And there's a force of gravity. And again, we know that this free body diagram has to be balanced because A is 0, so there has to be friction. All right, so we have that the normal force minus the gravity. Since all of these are just in component directions, I'm just going to go straight to the equations. Normal force minus the gravity equals 0. And the applied force minus the frictional force, kinetic, equals 0. So plugging in, the normal force is equal to mg, and the applied force is equal to mu times Fn. Substitute. And we get that the applied force is equal to mu times mg. Mu then is equal to the applied force divided by the weight. I gotta look back at my numbers here. I said 25 newtons and 45 kilograms. And again, no units because it's the ratio of two forces. So just like our trig functions are the ratio of two lengths, the coefficient here is the ratio of two forces, so it has no units. And for this example, we end up with, oops, typed something in wrong. 25 divided by 45 divided by 9. We get a mu of 0.057. All right, so there we've done a static and a kinetic now, and we'll call it there.